Hey there everybody, Mr. Deacon here, and in this video we are going to continue our discussion into applications of derivatives. So we're going to start off here with number 7 from our notes packet. It says the graph shows the position of a particle moving along a horizontal axis. So remember, whenever we deal with situations like this, a positive slope means it's moving forward and a negative slope means it's moving backwards. So let's take a look at the graph. All right, I'm noticing from the graph it looks like we have just a stagnant distance, so it looks like we're standing still for the first 2 seconds. And then it looks like I'm moving backwards because I've got a negative slope, moving backwards to a position at -4 on the number line. And then it looks like I turn around and I move forward for the next, 2 seconds. And then I stand still for that final little bit. One thing to keep in mind here, it looks like the y-axis is counting by 2s, so let's make sure we're staying cognizant of that. I can get the slope here if I go rise over run. Looks like I'm going down by 4 over by 1, so this slope would be -4. This looks like we're going up 1 and over 2, although we're counting up by 2, so up 2 over 2, so that's actually by 1. Okay. Let's see what questions this thing's asking. When is the particle moving to the left? Well, that means we have a negative slope. Well, this particle has a negative slope on that section of the graph from 2 to 4. So we'd write that as an interval 2, 4. When is the particle moving to the right? Well, that means we'd have a positive slope. If I look back at my graph, looks like right here from 4 to 6. We're going uphill. When is my particle standing still? Well, if it's standing still, we'd have a slope of 0, meaning a constant. So it looks like for the first 2 seconds and for the 6th and 7th second. So we have from 0 to 2 and also 6 to 7. Now, one thing to notice, 2 and 6 have parentheses and not brackets. That is because at this very instant, we have a corner, right? So it's not differentiable, so that means we can't really tell is the slope 0 or is it negative at that instant. So we can get infinitely close to it without actually knowing specifically what it's doing. All right, graph the particles. Ooh, typo. Particles' velocity and speed were defined. Okay. Well, velocity is just the rate of change. So here I've got a velocity graph. It looks like for the first 2 seconds, our function is just standing still. Then it looks like from seconds 2 through 4, we are going downhill, and our slope would be 4, because we're going down 4 over 1 is our slope there. And then we are going uphill, so we're increasing, we're moving forward, and the slope there would be 1, or up 2 over 2. And then we end with a constant velocity. Well, constant velocities have a velocity of 0. When we're doing velocity, it's possible to have a negative velocity. It's possible to have it's possible to have positive and negative velocity. Velocity is direction specific, meaning positive means you're moving forward, negative means you're moving backwards. Speed, on the other hand, is always positive. So speed is just the absolute value of velocity. So velocity indicates direction with positive or negative. Speed is just the overall absolute value number. So if I were to graph the speed function, essentially I would just take these negative segments here and flip them up above. So the absolute value of -4 meters per second would be a +4 meters per second. So this is what the velocity function would look like here. The zeros stay the same, the slope of 1 stays the same. Right here is where we have the speed flipped up. All right, part E. When is the particle moving the fastest? Well, that would be the steepest slope. I can tell from the original function, it kind of looks like this green segment here would be the steepest slope. Granted, it's moving backwards, but it's moving backwards fast. Or I could figure out, looking at either velocity or speed, which one's got the highest magnitude, so the furthest away from the x-axis there. When does the particle change direction? And it even tells us when it changes from positive to negative or negative to positive. So what we want to figure out is, when does it go from moving backwards to moving forwards? At what point does that happen? And that would be at 4 seconds. Some people get confused and think, well, hey, there's corners here and here as well. Why not those? Well, because it's not changing directions. Here, if I go from blue to red, it's moving forward, but then it just stops and stands still. So it doesn't change direction, it just stops. So for a change in direction, we have to see a sign change, a negative to positive or positive to negative. All right, so let's formalize some things. If you feel the need to pause the video, go for it. However, this is in your packets that have been provided to you. The first derivative tells you the slope of a tangent line of the function, which also tells you rate of change. Those go hand in hand. This is also helpful in finding the instantaneous velocity of a particle function, meaning at one specific time value for t, what is the slope at that moment? The derivative of position is velocity. So if I know a position function, I automatically can find the velocity function by taking the derivative. Velocity is direction specific. Negative velocities go backwards while positive moves forwards. If it's a constant number, that tells you how fast a particle is moving at that moment. The sign for velocity will tell you direction. So positives is going up or to the right or away from your starting point. If it's negative, it's going either down or moving backwards to the left or going towards the starting point. Acceleration is the derivative of velocity. So velocity was the derivative of position. Acceleration is the derivative of velocity. So I've got position. I've got velocity. Whoa, I can't spell worth a dang. Holy crap. And then I've got acceleration. So if you know the position function, you can derive that to get the velocity function. You can derive that to get the acceleration function. That tells us at what rate the velocity is changing. Well, velocity tells us at what rate the position is changing. Acceleration tells us what rate the velocity is changing. Units are typically written as meters per second squared, or some sort of distance over time squared. Speed is not used as frequently as velocity. Speed and velocity are very, very similar. The only difference is speed is always positive. Speed is just the absolute value of velocity. Velocity, however, we get that added benefit of knowing if we're moving forward or backward with a positive or negative sign. Okay. Next, if we're given a graph and we want to follow a particle's motion, forward means our slope is positive, backwards means our slope is negative, standing still, our slope is exactly 0. If we are changing direction, we switch from positive to negative or negative to positive. There has to be a sign change. So positive to negative, not to 0, positive to negative or negative to positive. And greatest speed would be the steepest slope. This also holds true for velocity as well. All right, so let's take a look. Here I've got a graph. Yay, graph. This says this is the graph of a position. Okay, so if this is a position graph, that means we start off, we are moving backwards. And then we stand still for a bit. And then we move forwards. And then we immediately turn around and we go backwards again. And then we stand still for a bit. And then we move backwards yet again. You'll notice these little numbers attached to each one. These are the slopes of the lines at those moments. So slope of 0, slope of 2, -2, 0, -4, so on and so forth. I've color-coded this as well, so anything that's red, that means we're moving backwards. Anything that's green, we're moving forward. Yellow, standing still. So let's see what questions are being asked. When is it moving to the left? Well, if it's moving to the left, that's backwards motion, so that would be anytime there's a downward slope. So we have 0 to 2 seconds, 8 to 10 seconds, and 12 to 13 seconds. When is it moving to the right? So moving forward, going uphill. That would be this stretch right here from 5 to 8 seconds there. And when is it standing still? For more than an instant, because you could argue right here at that very moment, for a split instant, it stopped moving. So we want more than a split instant. Well, that would be any time our slope is exactly 0. So from here, 2 to 5, and then again from 10 to 12. All right, onward. A particle is moving along a line, so its position at any time is given by the function t squared minus 3t plus 2. Now, one thing that we can get, as soon as I have my position function, what I like to do is immediately get my velocity function by taking the derivative. I have no idea if I'm going to need this, but who knows. The derivative function will be 2t minus 3. And then once I know that, I can also get my acceleration function, which would just be 2, the derivative there. Okay. Find the displacement, so change in position, during the first 5 seconds. So I need to know, where was it at the starting time? Where was it after 5 seconds? So plug in 0 for t, plug in 5 for t. The difference between these two values will tell me how far it has moved. So it started at 2, it ended at 12, that means it moved forward 10 meters. To find the average velocity, you find the change in displacement over the change in time. So we knew we advanced 10 meters, and it took 5 seconds to do that. That velocity was 2 meters per second. Find the instantaneous. Hey, that means we need the derivative function. We already found that. Huzzah! So the velocity function is just derivative of time. So we already found that as 2t minus 3. We're going to plug in 4 for t to see what we get. We would get 5 meters per second there. Find the acceleration. Well, the acceleration is just constant, right? I got an acceleration value of 2. That means regardless of whatever time value we plug in, the acceleration is always 2 meters per second squared, all the time. Next, at what values does the particle change direction? Well, let's think from this, okay? If I visualize what the graph of this thing would look like, we've got an upward opening parabola. And the y-intercept of that thing should have been 2, so maybe I didn't graph the best parabola in the world. The y-intercept is 2. There we go. Yay. Now, I have no idea where the min or max whatever is on this, but that's okay. What I do know is that we change direction the moment we go from downhill and switch to going uphill. And the moment that we change, our velocity has to reach a constant of 0. So what we're going to do is take our velocity and set it equal to 0. Well, we know the velocity function was 2t minus 3. Set that equal to 0, and we get 3/2 seconds, or 1.5 seconds if you'd rather write it as 1.5. So 1.5 seconds, that's when we switch from downward slope to upward slope. Then it says, when is our particle at a minimum? Where is it at a minimum? Well, again, we just found the minimum value because we have our x value, or in this case, t value. So the particle, looks like we need to find the position here. The particle would actually be at, let's see, if I plug in 3/2 to my function, we had 3/2 squared minus 3 times 3/2 plus 2. This would be 9 over 4 minus 9 over 2 plus 2. And that would be 9 over 4 minus 18 over 4 plus 8 over 4. And that would be at negative 1/4 meters. That's where we're at. All right, next one. Particle moves along the line. The graph of the position is given. Yay, graph. Anytime we have a positive slope, we're moving uphill. We're moving forward. Anytime we have a negative slope, we're going backwards. Anytime we have a constant slope, we're standing still. I don't know if you can see that yellow there or not. So here I've got negative slope. Here I've got a constant. Here I've got positive slope. When is the particle moving to the left? Well, left indicates backwards motion. So it is moving to the left from 2 to 5, and then again from 8 to 10. When is it moving forward to the right? Well, it starts off moving forward to the right, and then again over here, 12 to 14 seconds. When is it standing still? Meaning, when does it have a constant or flat velocity? So here from 5 to 8, and then here again from 10 to 12. Home stretch, people. Graph the velocity and the speed. Okay, so for this, I'm actually going to need to kind of plagiarize myself here. Bear with me, folks. So I'm going to steal that little graph there. All right, so it looks like we went through and at each little section, we identified what the slopes were. So the slope of this first bit is 1. The slopes for here would be -1, then at 0. So if we look at our velocity, we start off at +1, and then we immediately go -1, and then we spend some time at 0, and then we go -, 0, positive. So we're back at negative, then 0, then positive. I know these are constant velocities because this is a constant slope. Now with the speed functions, all that's different is that I'm taking what was negative values and just making those positive. So really just these two portions here got flipped up above because we're taking the absolute value of velocity in order to get speed. Well, no, when is this thing moving the fastest? Well, it looks like this stretch here at the end had the greatest velocity or speed. We could also look just at the graph. That's where we had the steepest line. So that indicates the highest speed. All right. Number 12, same concept. However, this one is showing velocity. So this is no longer just position. This is velocity. So if we start off moving downward, and then it's slightly less down, that's fun, and then switch to moving forward, and then hang out at a constant. What this really means is our velocity is decreasing. Our velocity starts off at 2 meters per second, now we're only going 1 meter per second, now we're going 0 meters per second, now we're going negative. So we have a positive slope, slightly less positive slope, slope of 0, now a negative slope, more negative, more negative. So if I'm visualizing a position graph, I've got a positive slope, a less positive slope, then a slope of 0, and now it's negative, more negative, more negative, more negative. Right? So that tells me it looks like we have some sort of a maximum occurring at 1 second. And then we have a sharp change. So we abruptly change the velocity. So we're going negative and then quickly snap back to be going positive. Okay, so let's see what questions are being asked. When is the particle moving forward? Well, it's going to be moving forward anytime our velocity is positive. So above the x-axis, we have the first second here, and then from 4 and change to 6, so from here onward, we have a positive velocity. When is it moving backwards? Well, that's anytime our velocity is negative. So our velocity is negative from -1 all the way up till 4 point something. When is the particle standing still for more than a split instant? So that means when is it camping out on the x-axis? Well, we'd have a velocity of 0 at 1 and at, we'll call that 4, but that's only for a split instant. It's not hanging out on the x-axis. When does it switch directions? Well, it changes positive to negative or negative to positive here at 1 and 4. And when is the particle moving at a constant speed? That's this last little bit here. When is it moving at its greatest speed? Well, at its greatest speed, we'd look for the furthest away from the x-axis. So it looks like, here we're moving at a speed of 2 meters per second, whereas right here at 3 seconds, we were moving at -3. So this should actually be 3 seconds. Now, if we want to graph the acceleration, keep in mind acceleration is change in velocity. So just like we did before with position, we're going to graph these each as little slopes. So the first 2 seconds, I've got a slope of -2. So right here, first 2 seconds, the slope was -2. So we have a constant deceleration there. Then from seconds 2 to 3, our slope is at -1. So between 2 and 3, we have a constant of -1. And then from 3 seconds to 5 seconds, we're going up 5/2, so 5/2, 2.5. And then we remain constant, so we have a acceleration of 0. All right, last and final one. We're given a position graph. Position graph means we're going backward, then we switch to forward, then we stay still. Then we move forward, stay still. We go backwards and stay still. So, when does the particle move forward? Anytime our slope is positive. So from 4 to 5, from 6 to 7. When does it move backwards? Anytime our slope is negative. So for the first 4 seconds, and then again from 9 to 11. When does it stand still? Anytime we are flat. So slope of 0. If the velocity is 0, that means we're not moving at all. When does it change direction? That means we change from a negative slope to a positive slope. So you need to see a sharp V corner right here at 4 seconds. And what was the particle's greatest speed? You could argue either the velocity of 2 or -2, so 2 meters per second. Now here we have a velocity graph. Anytime it's above the x-axis, it's moving forward. So anything up here, we are moving forward. Anything below, we are moving backward. Okay. When does the particle move forward? Well, for the first 2 seconds, and then again from 6 to 10. When does it move backwards? Anytime it's underneath the axis, so 2 to 5, and then again from 10 to 12, because it's underneath there. When does the particle speed up? Speed up, aka accelerate. When does the particle accelerate? This means when does it move away from the x-axis? So it looks like we're speeding up. We're accelerating between 2 and 4. But then from 4 to 5, we kind of come back in. From 6 to 7, we're breaking away from the x-axis, so our acceleration is getting more and more. And then we kind of stand still, and we're decelerating here. And then we accelerate again. This time we're accelerating in a backwards motion, so our velocity is becoming more negative. So from 10 to 11. When does the particle slow down? That means when does our acceleration, our velocity, when does that go back towards the axis? So it goes towards the axis from 4 to 5 here. Goes towards the axis from 0 to 2 here. And then again from 9 to 10 here. When is the particle standing still? Well, we'd have a velocity of 0 in that situation. So from 5 to 6. Some people might get confused and say, well, it's standing still from 7 to 9, right? No. That would be if this was a position graph. This is a velocity graph. So that is a constant velocity of 2 at that moment. And then what is the particle's greatest velocity? Well, the furthest away from the axis we get is right here at 2. All right, that's it. We've done it. You know the drill, folks. If you have any questions, please do not hesitate to ask. And as always, good luck, have fun, be safe, roll tide.